Here is Vasil Denchev from Google.
All right, thank you very much. My name is Vasil Denchev, and I'm going to talk about the computational value of finite range tunneling. This is work done at Google together with all of these other folks. Okay, so this is the outline of my talk. So first I'll go over some background on adiabatic quantum computation and quantum annealing. Then I'll talk about our idea behind finite range tunneling and how to use it to achieve a computational speedup. Next, I'll define our basic building block that we use for our results. We call this the weak-strong cluster pair. And out of the weak-strong cluster pair, we build larger problems called weak-strong cluster networks. I'll go over these too. And then I'll cover our benchmarking results, where we show the speedup of the latest D-Wave machine versus simulated annealing and Quantum Monte Carlo. And then I'll close with conclusions. Okay. So first, let's start with defining what is behind quantum annealing. So we're doing a quantum evolution here of a quantum system from some time t0 to some time t capital T. We're assuming here an ideal closed system, and later I'll talk about a more realistic model. The Adiabatic Theorem from quantum physics says that if we have an evolution time that is large enough, when we start in the ground state of our time-dependent Hamiltonian at time t0, we are going to end up in the ground state of our Hamiltonian at time capital T. So this large enough is defined in terms of the minimum gap in the eigenspectrum of the time-dependent Hamiltonian. The minimum gap is the closest that the ground state energy gets to the first excited state energy during the evolution. And the evolution time needs to be approximately proportional to the inverse square of that minimum gap. Okay. So how do we solve optimization problems using these physics? Well, we can start with an initial Hamiltonian that has a known and easily preparable ground state. And then we can encode the solution to our optimization problem in the ground state of at the final Hamiltonian, which we call HP here. So then all we have to do is initialize our system in the ground state of the beginning Hamiltonian, do the evolution for some time, slowly enough, and then we would be guaranteed to find the ground state of our problem Hamiltonian, and hence the solution to our optimization problem. So this is all idealistic in terms of running at zero temperature and having a closed system, but in reality, physical devices actually operate at finite temperature, so this thing is not as simple as described in the previous slides. What we get with temperature is what has been called quantum annealing, which is a quantum-enhanced optimization heuristic that exploits tunneling. But also, because of the presence of temperature, there can be thermal transitions that can happen as well. So the advantage of quantum annealing versus the gate model quantum computation is that it seems that we can have practical hardware implementations now, whereas gate model quantum computers will take more time to build and to implement the technology. So it's also known that quantum annealing is better than simulated annealing for problems with tall and narrow barriers, and this figure here tries to illustrate that. So when we have a difficult optimization problem with lots of local minima and large barriers, thermal annealing would have a hard time using thermal fluctuations to jump over a tall barrier, whereas quantum tunneling would be able to better deal with that barrier as long as the barrier is not too thick. So for tall and thin barriers, quantum annealing is better than simulated annealing, and that's what we're trying to leverage here. So D-Wave has been working on implementing this quantum annealing algorithm in hardware. In particular, the problem Hamiltonian of D-Wave is the Ising model, which looks like this. the difference, yeah, so it's not actually this general Ising Hamiltonian because in the D-wave machines, for engineering reasons, not all couplers are available. And also there's a limitation on the precision of the couplers and local fields that you see here in these terms. When we find the ground state of this Ising Hamiltonian, what we're doing is solving this optimization problem. So this is from the perspective of optimization. So this is what we would be doing if we were to find the ground state. And then in the D-wave machine, this is the whole time-dependent Hamiltonian. The beginning Hamiltonian consists of a transverse field applied individually to the, or altogether to the spins, to the qubits on the D-wave machine. And this is the annealing schedule. So initially the transverse field is high and then it gets decreased, whereas the problem Hamiltonian is switched off and then gradually it gets turned on. So this is the evolution from beginning to end. This is the hardware graph of the current D-wave machine that we have available for our use at NASA Ames. The dots here represent the qubits on the D-wave machine, and the lines represent the couplers between them. And in addition, there are local fields also that can be applied individually to each qubit. So this machine has 1,152 qubits, but only 1,097 of them are operational because the yield of the manufacturing process is not perfect. I have a short video here to illustrate the operation of D-wave. So first we have the transverse field applied uniformly to all the qubits on the chip. And then the transverse field is gradually turned off and the couplers and local fields are turned on, after which the qubits orient themselves in the z direction to assume their positions that should correspond to the ground state of the final Hamiltonian. And these up and down orientations correspond to logical 0 and 1, which can then be read off and represent the result of the computation. All right. So next, I'm going to cover what we understand here by finite range thermally assisted tunneling. So let's say we have some optimization problem like this. For simplicity, we've constructed something in 2 dimensions, which looks like this when projected to 1 dimension here. So tunneling can help us overcome, as I said, barriers with, that are tall and thin. So for example, going from A to B here can be done by tunneling, also with the help of temperature, by first picking up energy from the bath and kind of raising up a little bit, maybe halfway through up the barrier, and then using quantum tunneling to get through on the other side. And then finally, dissipating energy back into the bath and relaxing into the next local minimum. And then maybe we can do the same to go from B to C and so on. But in this particular example, we've drawn the barrier between C and D to be pretty thick, just to illustrate that quantum tunneling would probably have difficulty going from C to D because of the thickness of the barrier. So the probability of tunneling through this barrier would be small. So this means, I mean, this is a general feature of hard optimization problems, and means that quantum tunneling may not always be able to help, especially when we're limited to finite range tunneling. So if only a few of the qubits can tunnel together, then at some point their number may not be sufficient to really get through a thick barrier. So in that situation, we're interested in studying how quantum tunneling can beat approximation algorithms. And some of this work has already been started by other teams, and we think that is a very interesting question to explore in the future. Okay. So the basic building block that I mentioned in the introduction for the results that I'll show later is called the weak-strong cluster pair. And the goal of this basic building block is to use it to demonstrate how finite range tunneling can provide a considerable computational advantage. So this problem consists of just 2 Chimera unit cells. The Hamiltonian of this problem is this. It consists of 3 terms, 2 of which are describing what happens within each of the clusters. So we have some couplers and local fields in each of the clusters, and then this component describes the inter-cluster couplings that we have between the clusters. In particular, all of the couplings are set to 1, ferromagnetic. The local fields of the left cluster are set to some small positive value, and for that reason we call this cluster the weak cluster. The local fields of the right cluster are set to -1, and because of that larger magnitude of the local field, we call this the strong cluster. In the ground state of this problem, all of the spins should be pointing down. You can verify that, I guess, as an exercise. But early in the evolution, the weak cluster spins are misled by their fields because their fields are positive, so they're kind of pushing those spins to be pointing up, which is the wrong direction for the ground state. Later in the evolution, however, the intercluster couplings, these guys, they start to override local fields. But by that time, it's already too late because the weak spins have started, as I said, orienting themselves up instead of down. So at this point, in order to still find the ground state, the weak cluster spins need to tunnel. They need to turn themselves around altogether. And that corresponds to a tall barrier. It's possible to also do with thermal activation, but it's less likely. And there's a calculation for this that we have in a previous paper by Boishu et al. In Nature Communications that shows that, with a certain noise model with experimentally measured parameters on the D-wave 2x, that the tunneling transition would be more likely than thermal activation for this weak-strong cluster pair. So I'll go a little further, giving an intuition about how this problem works. So this is a plot of the mean field potential of the weak-strong cluster pair, with the axis being S. This one axis is the evolution parameter from beginning to end. This axis gives the tilt angle of spins in the weak cluster. So minus pi over 2 means that the weak cluster spins are oriented down, and pi over 2 means that they're oriented up, which is a false minimum. Okay, so as we start from here and follow the red line gives us the path of the instantaneous local minimum of this problem. And this is generally how the evolution would proceed. But at some point, approximately at s equals 0.18, we'll have a bifurcation point. And by that we mean that in the potential, we have a second local minimum starting to form. Okay, and then it turns out that actually the global minimum forms on the other side, which is this along the blue line. But the system has already started following the red line here, and by the time it's apparent that the global minimum is somewhere else, the system is already behind this barrier that has already formed along the green line here. So in order to still reach the global minimum, the system has to tunnel under the barrier along the green line, or have a thermal activation over it, jump over it thermally. And again, as I said before, it's more likely that the quantum tunneling will be successful rather than the thermal activation. And we have verified this experimentally. So we tried increasing the temperature gradually of the D-wave machine and running these weak-strong cluster pairs to verify that a method that works with thermal fluctuations like SVMC actually has its probability increased with temperature, because that makes it easier to jump over that barrier thermally. But a quantum device like D-wave, its probability of success goes down with increasing temperature, because the tunneling probability gets decreased that way. And this is also in accordance with in agreement with two simulations two quantum simulations called NIBA and Redfield that don't have any fitting parameters, but are using parameters, again, experimentally measured noise parameters from the D-Wave machine. So this is strong evidence that this is really what's happening in the D-Wave machine, and that tunneling is playing a functional role there for solving successfully the weak-strong cluster pair problem. All right. So out of the weak-strong cluster pair, we build larger problems, which we call the weak-strong cluster networks. This is a crafted problem, and we have specifically designed it to, like this, to have tall and narrow energy barriers so that we can amplify this effect that we saw in the weak-strong cluster pair problem. Basically, the way we construct it is we take a number of weak-strong cluster pairs that we can find on the D-Wave graph, and we connect the strong clusters of them in a glassy fashion, which means that we set the couplers between them either O2 + 1 or O - 1 at random. So here, these black unit cells are the strong clusters of a number of weak-strong cluster pairs, and their weak clusters are just hanging off on the side, like you can see here. And we connect the strong clusters together by randomly choosing, for each pair, randomly choosing whether to set their couplers to O - 1 or O + 1. And because that's similar to maybe a spin glass problem at 0 temperature, if you collapse the unit cells to single spins, we call this kind of a spin glass kind of way of connecting the strong clusters. So this is the small version of the problem with 180 spins on the D-Wave graph. We have constructed larger versions like this. This is still larger, yet larger. And then this version covers almost all of the graph of the current D-Wave machine. So at large sizes like this, we're suspecting that the glassy backbone of the problem is dominating the computational hardness. This is also explored by a recent paper by Helmut Katzgraber's team, which you can find here on the archive. So it's probably the case that finite range tunneling would be insufficient for reaching the ground state when the glassy backbone is dominating the computational hardness. And again, here I want to mention studying approximability in this case. So even though at some point we might not be able to reach the ground state, we're still interested in maybe finding good approximate solutions that can compete with classical approximation algorithms. So that's an open question for now, although, yeah, we've started studying it, and other people have started studying this. Okay, so now we come to the results of this study. I'll first talk about what we measure and how we measure it, and then I'll show the main results. So our metric here is the total annealing time for finding the ground state with 99% success probability. For the D-Wave machine, we fix the annealing time to 20 microseconds. That's the lowest possible, and we fix it to the lowest possible because it's actually not optimal. I mean, if we can run the D-Wave machine faster, we would be achieving better results. And then we measure the total annealing time to reach the 99% target probability, which is according to this expression. So this is a 20 microsecond per run annealing time. This is the per run success probability of the wave, and this log expression gives the number of repetitions that need to be done in order to achieve the target 99% success probability. Okay, for simulated annealing, we have some parameters to vary. We try to find the optimal per run annealing time, which is given by optimal number of sweeps times the problem size times a constant of 0.2 nanoseconds that we assume for the best possible classical hardware that can be done. So we optimize the number of sweeps per run. And for example, we find an optimal number of sweeps of something like 50,000 for the median instance at the largest size of the weak-strong cluster networks. We also vary the initial and final temperature of simulated annealing in order to find the optimal annealing schedule. And again, the total annealing time is given by a similar expression where we have the optimal per run annealing time and the optimal per run success probability. So we report the single core annealing time of simulated annealing, and we know that simulated annealing repetitions can be trivially parallelized. For QMC, so QMC is a simulation method that samples or tries to sample from the Boltzmann distribution of a classical Hamiltonian, which approximates the transverse field Ising model. So we use it as a solver whose performance is expected to correlate with the performance of an ideal physical quantum annealer. But QMC has a large constant prefactor when we run it on classical machinery, so it's still not a replacement for a physical quantum annealer. So in QMC, we also have parameters to vary and to optimize. We optimize the optimal per run annealing time according to this expression here. And as well as the number of sweeps per run. We fix the inverse temperature to be equivalent to 4.8 millikelvin to still keep it realistic for physical devices. And we find that running it with open boundary conditions is better than periodic boundary conditions. So there are more details related to these parameters in this archive paper for anybody who's interested. So one thing that we found in our experiments on the weak-strong cluster networks was that QMC was generally doing more sweeps per run in its optimal regime and achieved larger per run success probability than simulated annealing. So if we take this as a confirmation that actually quantum tunneling is essential for this problem, because simulated annealing cannot do quantum tunneling, it can't do much better than just kind of random sampling, so that's what it mostly does. Whereas QMC is simulating the tunneling, or attempts to simulate the tunneling that a quantum device would do. And that's why it's able to achieve a higher success probability in its optimal regime. So that's an interesting thing to observe. Okay, so this is the expression for the total annealing time of QMC. And again, we report single core annealing times for QMC as well. And we know that the QMC repetitions can be parallelized also. These are the main results that we find. I guess Hartmut already introduced you to this figure in his introduction. So here we find that single core simulated annealing and QMC times are 10 to the 8 times larger than the D-wave 2x times on instances of the weak-strong cluster networks of sizes up to 945 variables. We also find it interesting that the error bars of D-wave and QMC are larger than the error bars of simulated annealing. So we interpret this as revealing the sensitivity of the individual instances to the glassy backbones of the weak-strong cluster networks. The reason why the simulated annealing error bars are much smaller is that simulated annealing is already severely stumped by the weak-strong cluster pairs themselves, okay? Whereas the quantum methods, they can successfully solve the weak-strong cluster pairs individually, and they only get stumped by the glassy backbone that becomes more dominant as the problem size increases. And this also occurs more often with increasing problem sizes. Okay. So in conclusion, we found that finite range tunneling can provide considerable computational advantage. So we saw an impressive 8 orders of magnitude speed up over simulated annealing and Quantum Monte Carlo. Of course, besides these classical algorithms, there are other classical algorithms that can perform much faster on not just the weak-strong cluster networks problem, but on pretty much all Chimera problems. And in particular, for the weak-strong cluster networks problems, this is kind of trivial for classical algorithms because we can see the clusters by eye, right? But the point here is that these classical algorithms, like the HFS and cluster finding algorithms, they will no longer be able to work successfully as we increase the connectivity of our hardware graphs. And for sufficiently dense graphs, pretty much any classical algorithm would have a very hard time competing here. We also found that the glassy backbone of the weak-strong cluster networks dominates at large sizes. And we note that finite range tunneling can be insufficient for reaching the ground state in these cases. And in other cases too, as I talked in the beginning, when we have thick barriers, finite range tunneling will be insufficient. But then studying approximability may be very fruitful to do. All right, that's all I have.
Okay, thank you very much. Okay, please. Yeah.
Can you go to the previous picture, please?
Which one?
The previous slide, the picture, the graph.
This one?
Yeah, so you mentioned that the advantage of quantum D-wave versus quantum Monte Carlo is just prefactor. But if you look at harder problems, like 85 or 75% percentiles, quantum Monte Carlo actually fails. So it's not just prefactor, it's more than prefactor for harder problems. Am I right, or am I missing something?
You're saying that QMC fails more than D-wave fails?
For harder problems, for 85%.
Well, it's hard to see here because we don't have data really for the higher quantiles of QMC for the larger sizes. It might be the case. This was so computationally intensive that we had to stop our runs at some point, and we don't really have the data there. But
there is a hope that it's more than three factors. There's something.
Yeah, maybe.
Okay,
yeah.
Thanks.
Sure.
Hello. I was wondering if you can go back to the slide where you have Redfield, NIBA, and the D-wave with error bars.
This one?
Yes. So I wonder if you've tried to use a more accurate quantum mechanical simulation, because both Redfield and the non-interacting blip approximation, those are both very risky methods to use when modeling open quantum systems. They both fail in a wide range of regimes.
Okay. Yeah, I wasn't the one actually that ran these simulations, so I don't know if there's somebody here that
would
can
I
answer
ask
this
about
question.
that?
Yeah. Yeah, Sergio.
Okay. Okay.
So we believe NIBA, the approximation, is the most accurate method we know of. If you think there is a more accurate method, I would like to know. But
yeah.
On this particular regime, and it actually took a long time to develop that with Mohammed and Vadim and a bunch of people.
I see. Okay.
So we believe that for this problem, where you can look at the details on the paper, not this. Actually this paper, we think is pretty accurate. But if you think you can propose something more accurate, that would be interesting to know. We're not aware of anything more accurate than that.
You can
and we
use
think
the open source path integral code FineDyn, which stands for Feynman dynamics, and you can try that. Maybe it will be closer to the D-wave experimental value.
Okay, maybe we can talk about it later.
Okay.
Yeah.
Thank you.
Okay, we still have several minutes for questions. Yeah, please come.
Can you tell us a bit more about what the glassy background means in the large instances of weak strong clusters?
Yeah, this is just the arrangement of the strong clusters here. As I said, we're connecting them in what we call glassy fashion. And all that means is that we just randomly pick the sign of their couplers, whether that's -1 or +1. So you can kind of view it as a spin glass at 0 temperature. If you collapse each unit cell to a big spin and connect these spins like that with random couplings, that's the only reason why we call this the glassy backbone of the problem.
Okay.
Yeah.
Thank you.
Yes, please.
For the simulated annealing results, could you explain the annealing schedule that was used and perhaps what other annealing schedules might have been considered?
What other parameters might have been considered?
The annealing schedule for simulated annealing.
Yeah.
Which annealing schedule did you use?
Yes, so for simulated annealing, we used, I think it was a linear schedule that decreases the temperature in linear steps, basically, right? Yeah.
Did you consider any others?
Any other schedules? I think we've tried like an exponential schedule also, yeah.
Okay.
But it doesn't seem to make much difference.
Those both tend to freeze rather quickly. So there might be other schedules that might do better.
Okay, yeah, I think we have a reasonably high confidence that we've, tried all the good schedules. But yeah, maybe there is something more to be done here. Yeah. Okay.
Thanks.
Thank you.
So may I myself ask a question?
Yep.
You said that for larger systems, Quantum Monte Carlo didn't reach conclusions with high accuracy. And I heard a rumor that you spent a very large computational effort to simulate the system for simulated annealing and quantum annealing. And
Yep.
at the time you spent a good chunk of the Google computational power on this
Yeah.
project. Is that true?
That's right, yes. So yeah, the reason why we don't have any more data points here for the larger sizes of QMC at the larger quantiles is that, we already spent quite a bit of computational time on getting the other data points, and this would have taken a lot longer. So it was quite, you can imagine that Google has a lot of computing power, and we did employ a significant portion of it for just computing this single plot figure here. Yeah.
So energy-wise, D-Wave is more efficient in this sense.
Sure, yeah, by far, yeah. Yeah.
Okay, well, that aspect may be important practically.
Yeah.
Any other questions or comments? Okay, if not, let's thank the speaker once again.
Thank you.